This playlist deals with some aspects of Eurocode 2 version 2023. Watch this channel or playlist for further selected topics. This video deals with clause 11, detailing of reinforcement, part 7, and it's about anchorage and in more detail about the lap lengths. To prevent large cracks parallel to the lapped bars, this will be okay. There will be no large cracks if the diameter of the lap bars is smaller than 20 millimeters, or the percentage of lap bars is smaller than 25 millimeters. If this is not the case, there is a minimum amount of transfer reinforcement or confinement reinforcement needed. And if more than 50% of the reinforcements are lap bars, then the confinement reinforcement is needed. So this is very strict. This condition, the first condition, in most cases you have diameters bigger than 20 millimeters or equal than 20 millimeters. Percentage of lap bars is in a lot of cases 100% for starter bars, for instance. So we have to fulfill this. So it means that we need transfer or confinement reinforcement, but the 50%, so when you are 100% lap bars, you always need confinement reinforcement. So this is rather very, very strict. For tension laps, you have two situations. First, I have to tell you transfer reinforcement because this is the lap. This is the lap length. Then you need at least 5 bars transfer reinforcement, which is 1, and 2, which is the confinement reinforcement, stirrups, for instance. So this is a transfer reinforcement. This is the confinement reinforcement. The horizontal part is also transfer reinforcement, but confinement, you always need a vertical element. So for starter bars, this is a little bit complicated. This is for tension laps, those two situations. For compression laps, you will have here the transfer reinforcements. Then you need at least over a certain distance 3 bars, and here 2. And for confinement reinforcement, you will have the same type of situation. And the clear distance is the maximum of 2 feet times 50 millimeters. So they talk not center to center, but the clear distance, which is this clear distance here indicated as 3, which is the end of the lap length and the start of the confinement reinforcement, not to the center, but on the side of it. The anchorage length, needed anchorage length or lap length, I must say lap length because it's LSD, in tension or compression must be bigger than KLS times BD with KLS 1.2. So you need 20% more anchorage for a lap. But when you have lapped bars, then you can see, for instance, that this lap bar on the left-hand side, this is the bars which are already there. This is the new bar. This is one which is already there. Then CS must be the sum of the two clear distances. This is again another definition of CS. And CS is used to calculate CD. And CD is used to calculate LBD. Now this is very surprising, this coefficient 1.2, because in Eurocode 2 version 2004, KLS in fact equals alpha 6, and that's the alpha 6 of the version 2004, was 1/5 of the square root of the percentage of laps. So to give you some figures, when you have a more than 50% laps, this factor is 1.5, not 1.2, but 1.5. When less than 25% is lapped, this coefficient is 1. So the coefficient KLS was a function of the percentage of laps, and now suddenly it's not. Quite strange. Now they make it quite complicated. You have two main cases: away from plastic hinges locations and across plastic hinges locations. So this is already a problem. When do you know? How do you know that? How do you know it's a plastic hinge, yes or no? It's not a definition of it. I would say a plastic hinge is where the tensile stress in the rebars is equals to the design value of the yield strength, but that's in most cases. So in most cases you are across plastic hinges location. Again, there was no definition what this means in the code. In the first one, when you are away from plastic hinge locations, then even for compression or tension, you can have 100% laps and you can calculate the lap length with sigma SD. So that's nice. So there is no factor 1.2. You would think so, but this is not the case. This is only for calculating LBD. It has nothing to do with the factor KLS. So for calculating LBD, you can take sigma SD even if you have 100% laps. Then for tension, in the case that you are across plastic hinge locations, then when you need confinement reinforcement, when you use 100% laps, and you can calculate LBD with sigma SD. For linear elements, when you have smaller than 35% laps, you can calculate with sigma SD. For planar elements, you can calculate with sigma SD from when you have less than 50% laps. Or you can choose 100% laps, but then you have to calculate your anchorage length LBD, this one, with 1.2 times sigma SD. So you have an increase in LBD to compensate for the percentage of laps. When you look at it carefully, then you see immediately this is in contradiction with what we've seen in the previous slides. In clause 11.5.2.10, it was stated that from 50% onwards, you need confinement reinforcement. Now, this is saying 100%. So it's not really clear. And these are other percentages. Also, this says that you can have 100% laps, but you calculate with 1.2 sigma SD, which is in contradiction with 11.5.2.10. So this should be clarified. Look at the lap lengths in plan view. Then you will see you have a distance one between two laps, and you have within one lap the distance between the two bars. So the clear distance between adjacent laps must be bigger than the maximum of 2 times the diameter and 20 millimeters. What will this formula be when you have two different diameters? Then I suggest you take the biggest of the two, the biggest diameter of the two. And 2 is the clear distance between lapping bars, which is the maximum of 4 times the diameter and 50 millimeter. And then you can stagger your lap lengths to avoid the 100%, for instance, laps. This is 100% lapping. This is staggered. So most likely 50% lap lengths. Then you see that you have some geometrical conditions to it. Now let's look at the lap length of straight bars in more detail. Straight bars is for tension and compression laps. Then you see that LSD is equal to KLS times LBD and must be bigger than 15 phi. So In 11.522 part 2, they only said that the LSD must be bigger or equal to KLS LBD. And now in the table 11.3, they say it's equal to and it must be bigger than 15. So why did they not mention it before? Why suddenly now in a table? So you can easily overlook this, huh? Because you can see this, you use this formula, and you forget about 15 phi. LBD here is according 1142. 1142 means formula 11.3, and with KLS is equal to 1.2. For bends and hooks, again, the lap length, LSD, for bend and hooks, in tension laps only, not in compression. Compression is not allowed here. LSD is KLS LBD bigger than 15 phi. Again, LBD must be calculated for bars, the anchorage length of bars with a standard hook, which is according 1144. KLS is again 1.2. So that makes it easy. Huh? For lap lengths, it's always using the formula of anchorage length multiplied by 1.2. For loops, for regular loops, tension laps only, you see that this is the definition of LSD for loops, must be bigger than the mandrel diameter plus 4 times the diameter. Huh? The mandrel diameter plus 4 times the diameter of the bar. What happens if you use loops with different bar diameters? That's not stated, but it should be, I would take it as a safe side, the maximum size of it. And LSD is according 1154. We will just see how this will be done. This is the loop, and you must take care with this figure. You see that this is the mandrel diameter, and you see that the area which is indicated here with the different dots, it's AC, concrete area. AST is the transfer reinforcement, the interlocking reinforcement within the loops. This is a loop doing this, and the loop doing that. With the force T1 and T2, T1 and T2 can be different when there is a bending moment involved, not only tension, but also a bending moment. But in most cases, T1 is equal to T2. And AC, when you look at this picture, you think AC is just the area within the loops, which is not the case. It is the area within the center lines of the rebar. So you take the center line of this rebar, and that's the dotted area. This plus this. So don't make this mistake. This what I'm saying here, it's not mentioned in the code, but the code gives you a formula to calculate AC, and then you can see what they have done. To avoid brittle failure, a minimum amount of confinement reinforcement, AST, should be placed in a double symmetric configuration. It means this and this should be symmetric according to the y-axis and the x-axis, double symmetric. And this confinement reinforcement is equal to this formula 11.16. You see, AC plays an important role in calculating this confinement reinforcement. We can now look at the top view of this U-bar laps. And to avoid crushing of the concrete within the U-bars, then you must limit the total force, T1 and T2, you take the maximum of it, and it must be smaller than TRDC given by this formula, 11.13. The distance between two U-bars lapping must be smaller than 0.5 LSD, otherwise it will not work well. The concrete cross-section AC, like we talked in the previous slide, is given by this formula. You see 0.21, which is a little bit strange when you see it like that, but in fact, it's in fact 1 minus p over 4, which is almost equal to 0.21. I do not understand why they do not use 1 minus p over 4 instead of 1.21. When omega is bigger than 0.5, then the factor KST, this one, is 1. And when omega is smaller than 0.5, then KST is equal to 4 omega times 1 minus omega. And omega is given, it's like reinforcement, mechanical reinforcement ratio, a modified mechanical reinforcement ratio. AST is the confinement reinforcement. Now, when you look again from the top and you have multiple laps of U-bars with the interdistance now CS is then equals to the mean value of the two clear distances. And it must be smaller, the sum must be smaller than LSD over 2. Then the maximum force that can be taken by those laps must be smaller than TRDC, like we have seen in the previous slide, but multiplied by the coefficient ns minus 1. And ns is the total number of U-bars in that lap. So here in this example, for instance, you have 1, 2, 3, 4, 5. ns is 5 in this case. And TRDC is about the total force, the total force on the left, total force on the right. Then you have also lap lengths of headed bars. Those lap lengths can be calculated according 1155. I will not go into detail into that because this is for tension and compression laps, but I will not go into detail because I've never encountered this in my 35 years career. I've never encountered a lap length of headed bars. But when you have the case in your project, then you should go to 1155. And then we have the lap lengths of intermeshed and layered fabrics that in fact we have seen already because this is a straight bar laps, but with confinement not confinement, but with transfer reinforcement. And this is for tension and compression laps. And the total length of the lap is KLS times LBD. That must be bigger than the maximum of 15 times V. And then you see 250 has been added to that when it is about intermeshed and layered fabrics. And KLS is 1 point. And finally, when we make a comparison between the anchorage length and the lap length with the version of Eurocode 2 2004, then out of the previous slides, we have seen this graph, which gives on the x-axis the tensile stress, and on the y-axis the ratio 2023 divided by 2004, and this for different rebars. So the rebar decreases from top to bottom. Then we've seen for anchorage lengths that for the rebars, which is situated in this zone, the anchorage length is less than the one prescribed in 2004. But in most cases, it's in all cases, when you have a yielding of the steel at 435 megapascal, that's the dotted line, you will see that all those values gives you more than one. So you need more anchorage lengths than was foreseen in the code version 2004. Now, when you go to lap length, you've seen that in the previous code, the lap length was much higher, or in some cases much higher, and in the code 2023, it's less. So when we compare those two, it's the same scale, then we compare those two, lap length with anchorage length, then you can easily see that from diameters bigger than 14, then the lap length is bigger than the one prescribed in the version 2004. But when we are working at a yield stress of design value of the yield stress of 435 megapascal, then you see that only for the large rebars, 25 and 32, then you need more lap lengths. But for the other rebars, you need less. So this is a little bit strange because this is just the opposite from with anchorage length. So you need more anchorage length for the version 2023, but less lap length for the version 2023. Not very logic, but it's stated like that in the code. You see also the difference. It's 25% or 20% more. And you see that for a bar of diameter 32, you have a lap length ratio difference of the ratio of the lap lengths needed is 1.5, and for the anchorage it was 1.9.